So what I thought we'd start off by doing with NMR, because you've done a lot of this already, is look at why NMR works. So look a little bit about the theory of NMR before we start going about the information it gives us. NMR is such an important technique, not only if you go into chemistry, but also if you go into medicine. What do you use it in medicine for?
MRI.
Yeah, MRI. MRI is just like a big NMR machine. Why don't they call it NMR?
It scares people.
Yeah, it scares them senseless. Because we use the word nuclear.
It's magnet, isn't it?
Sorry?
It's magnet.
Yeah, that's how NMR works. So, why does NMR work? Well, the reason is some nuclei have this property called spin. Not all nuclei, but some, and the two that we look at are hydrogen, 1, so that's hydrogen which has got 1 proton, no neutrons, and carbon 13, so that's the less common isotope. Carbon 12 is the one that makes up most things, and then we've got carbon 13. So those two have things called spin, and they, because they spin, so you can think of them as spinning, they act as baby magnets. So they are spinning around, and because they spin, they act as little baby magnets going around. Not particularly interesting, but because they're baby magnets, they can either be pointing, they've got a north and a little south pole, so they can either go like that or they can swim around. So, how do we work? Well, we put our sample in a mega magnet, and that causes an energy difference between their states. So we'll have a look at that now. So, I'd like to do a few notes on this if you don't mind.
Yes, please.
Okay. So some nuclei have this property called spin. This makes them act as baby magnets. So they have a little north pole and a little south pole, like so. So how can we do this? So for NMR, the way we work it, we dissolve the sample that we're interested in. So we would dissolve the sample to be analysed. In a solvent, and we'll talk more about what solvents we use in a minute, and place it in a very powerful magnet. Now the magnet is really cool because it's a superconducting. So the way you do it is they start it off and they keep it, because it's superconducting, they have to keep it very cold. So they put it in a jacket of liquid helium, and the liquid helium is in a jacket of liquid nitrogen to keep that cool.
So cool.
So you keep it very, very cold. And so liquid helium is very expensive. So you keep the liquid nitrogen topped up, which is quite cheap. You keep that up. If the tragic thing would be if the temperature gets too high, so if the hydrogen all evaporates or it gets too low, which can happen, you lose the magnet because it's no longer superconducting, so it's gone, and then you have to restart the whole system up.
How do you get more helium?
So we've got this in a really, really powerful magnet. So if I say, so I've got a big arrow like so, that is my powerful magnet. So my baby magnets, which are in my sample, so they're my little hydrogen nuclei, they have a choice, pretty much. If I pop them in, what are they going to do? If they've got little north-south poles, generally, if I don't do anything, they all line up. So my baby little nuclei all line up in my sample with my magnetic field, because that's the lowest energy state. They all go, oh, I'm in a north to south, so we all line up so that we all match.
How would they line up? Would they repel? Yeah, if that option is.
So they all line up, very powerful magnet. So what do we do this? So we say most nuclei line up with the magnetic field, like so. Okay, so what do we do? When we run an NMR, we fire at it radio waves. Radio waves are very, very low energy because there's not a huge energy state. We then fire So we use radio waves
Can I do this going down?
to, that's fine, to flip the nuclei. So the nuclei absorb the radio waves and go into a higher energy state.
Why flip the radio? Flip the nuclei? What do you mean? Like,
Okay, so I'll show you.
turn them
So
over?
yeah, so that's my powerful magnet.
Oh,
Like
so
so.
you go.
So now they flip the other way. So they now are acting in the opposite way to the magnetic field. So they've gone into a higher energy state. They're no longer lined up. So we measure, basically what you've got on your NMR is we measure the frequency of radio waves that causes each type of nuclei to flip to a higher energy state. Now you know this frequency that we measure, which causes a flip, you know that as the chemical shift.
Yeah.
This is called the chemical shift. However, it's a bit odd. You would expect it therefore to be measured in hertz, wouldn't you? If it's a frequency. Yeah, but we don't because the differences are so small. It is measured in ppm, parts per million. ppm, parts per million. Because it's so small. So by doing lots of this, we find that different chemical environments cause the nuclei
What? What's she doing?
She's scared of the camera.
change
Oh!
energy states. At slightly different frequencies. So I've put in brackets by frequencies. Obviously, you know that as a chemical shift, which are on the data booklet. At A level, there are 2 types of NMR you need to know about.
How long is this?
There are many, many more. You have carbon 13 NMR. That is the easiest. What does carbon NMR, what information can I get from a carbon 13 NMR?
How many environments are there?
How many environments?
What type they are?
Structures, the type of structure.
How many carbon environments? And I can work out structural information from that. And the type of environment, type of chemical environment.
Should we shut the windows?
That's all I can get, really. Carbon 13 NMR is simple, so people like it. However, the powerful boy is hydrogen NMR or proton NMR. No, it doesn't matter. Most people call it proton NMR. Hydrogen 1 NMR not only gives you the chemical environment.
How many hydrogens are in that?
Yeah. So it also which you get from the
Intensity.
the first one we get from the chemical shift. I also get the number of the ratio of hydrogens.
Number of hydrogens in each extra carbon.
Yeah, ratio of hydrogens in each environment, which I get from intensity. And finally, I get the number of hydrogens on neighbouring carbons, and I get that from splitting. So hydrogen NMR far more powerful, and because it's more powerful, it is far more complicated.